With the advent of internet and wireless communications, telecommunications became an inseparable part of our lives. With widespread use of internet applications and cellular radio, the number of users and user terminals increased drastically. As a result, transmission frequencies have shifted to higher frequencies in order to meet the increasing demand for higher data traffic. In the meantime, novel communication techniques are developed to provide reliable communications in fading wireless channels. As seamless wireless connectivity becomes increasingly important, Mimo systems are poised to become a major player to provide high data rates in fading channels. In this episode, we will discuss this breakthrough technology that promises unmatched performance, reliability, and speed. Before we continue, make sure to subscribe for more videos on emerging information and communications technologies. Fading effects. In multipath fading channels, the transmitted signals reach the receiver by following multiple paths due to scattering from obstacles on the propagation path. This results in constructive and destructive interferences of the scattered signal components at the receiver, thus multipath fading. Fading causes serious degradation in system performance. This figure shows the bit error rate, or BER, for binary phase shift keying in a Nakagami M fading channel as a function of ratio of energy per bit, EB, to noise power spectral density, N0, for various values of the fading parameter M. EB over N0 corresponds to the signal-to-noise ratio, or SNR, for digital signals. Nakagami M fading model is widely used in modeling fading channels. The curve for M equals 1 applies for Rayleigh fading, whereas the curve for M equals infinity represents an additive white Gaussian noise, or AWGN channel. The bit error rate due to fading is observed to be much worse than in AWGN, since it requires much higher transmit powers to achieve the same bit error rate. However, as M increases, the channel evolves from Rayleigh fading channel to a Gaussian channel. The bit error rate performance in fading channels degrades by more than 40 decibels at operating bit error rate levels. This means that transmit power must be increased by a factor of 10,000, for example from 1 watt to 10 kilowatts, to achieve the same bit error rate you would observe in an AWGN channel. Antenna diversity. Using channel coding, higher transmit powers and/or higher gain antennas are either not practical or not allowed due to health regulations or interference considerations. Such large performance degradations due to fading can be circumvented by diversity, which is based on transmission or reception of the same signal using independent channels in time, frequency, space, or polarization. Antenna diversity refers to transmission and/or reception of the same signal of a single user by multiple antennas. Since independently fading channel gains do not fade simultaneously, the receiver can utilize the independently fading copies of the same signal to make more reliable decisions about the transmitted symbols. Diversity leads to higher data rates and improved link reliability due to increase in the array gain, which is its normalized SNR, and the diversity gain, which mitigates fading and reduces the bit error rate for a given output SNR. This figure shows the block diagram of a receive antenna diversity where the SNRs of signals received by N receive antennas in diversity channels with random channel gains are summed. This is called maximal ratio combining, or MRC. This figure shows the bit error rate for binary phase shift keying, or BPSK modulation versus branch EB over N0 expressed in decibel for various values of N, the number of diversity branches for a maximal ratio combining system. There is a rapid decrease in bit error rate with an increase in the number of diversity branches. However, this decrease slows down as N exceeds 5. For N exceeding 5, the MRC system in a Rayleigh fading channel outperforms the corresponding bit error rate in AWGN channel. For N equals 5, the bit error rate performance is improved by more than 30 decibels due to MRC diversity combining. This implies a 1,000-fold saving in transmit power. One may thus conclude that MRC diversity mitigates Rayleigh fading effects, and provides a unique opportunity to communicate more reliably at higher data rates. Multiple input multiple output, or Mimo systems. This figure shows the block diagram of a Mimo system with NT transmit and NR receive antennas. Mimo systems are simply generalization of transmit and receive antenna systems. Mimo systems enable communications between multiple users, utilizing multiple antennas at the transmitter and at the receiver to benefit diversity, beamforming, and spatial multiplexing. Mimo systems have more antennas than transceivers. A transceiver may thus utilize multiple antennas for improved performance. This is a cost-effective approach since antennas are in general cheaper than transceivers. The Mimo receiver processes the outputs of NR times NT diversity branches to mitigate channel fading and to make better decisions about the symbols transmitted. This figure shows the bit error rate for BPSK modulation as a function of EB over N0 per branch for various Mimo sizes. The increase in Mimo size leads to drastic improvements in burr performance for small Mimo sizes. For Mimo sizes exceeding 3, the bit error rate performance is better than in AWGN channels. This implies that the fading is mitigated. As Mimo size increases, however, the bit error rate performance improvement slows down because the diversity benefits diminish as the number of diversity branches, given by NT times NR, exceeds 10. Note that the increased overhead due to channel estimation may be a serious issue for large Mimo systems. Massive Mimo. Massive Mimo refers to a Mimo system consisting of many smart antennas. Smart antennas are embedded in radio transceivers, and are managed appropriately. The use of massive Mimo in the millimeter wave band is advantageous since hundreds of antennas can be packed into a small space and provide high gains. In the millimeter wave band, wavelength is shorter than 1 centimeter, so a 100 x 100 Mimo system can be packed into an area less than half a meter times half a meter with half wavelength antenna spacings. They can be integrated into boards and chip circuits. CMOS production technologies offer substantial reductions in cost and size. In addition, power-efficient circuits, smart antennas, and millimeter wave band devices enable the use of wider bandwidths. Because millimeter wave signals cannot penetrate walls and other obstacles, frequency reuse distances are shorter in this band. Due to the high data rates, the channel may experience frequency selective fading. This may result in more complex receiver designs, but also with additional diversity benefits. Analog beamforming. Analog beamforming refers to the transmission of a single data stream using multiple antennas in line-of-sight links. Phase shifters used at antennas ensure co-phasing of diversity branches at the receiver. As a simple example of analog beamforming, we consider beamforming in the angular direction defined by theta equals theta 0 using 2 antennas. To this end, we shift the phase of the second transmit antenna compared to the first one by xj dsi and theta 0. This compensates the phase difference due path length difference, R2 R1 equals dsin theta, in the direction theta equals theta 0. The two signals are thus co-phased at the far-field receiver, and the received field strength is doubled. However, since the transmit power is equally divided between the two transmit antennas, the received signal strength is actually increased by only a factor of square root of 2. Since the received signal power is the square of the received signal strength, it is doubled when compared to single antenna transmission. Analog beamforming with N antennas increases the received SNR, hence the array gain, by a factor N. Scanning arrays commonly used in radar systems can scan their beam direction by changing theta 0 electronically. Digital beamforming. A digital beamformer, also known as a precoder, is a generalization of an analog beamformer. Analog beamforming is implemented by phase shifters in antennas, whereas digital beamforming is implemented by phase changes in signals that compensate for random channel gains. Massive Mimo systems may use digital beamforming to spatially multiplex multiple data streams to users on multiple beams with higher array gains. Digital beamforming may also be used for interference cancellation. Beamforming algorithms estimate the direction of arrival of user signals in azimuth and elevation to carry out appropriate signal processing required for beamforming. Switched beamforming refers to the formation of multiple beams covering all directions, and one or more beams can be switched on when needed. Adaptive beamforming is more suitable than switched beamforming because of its ability to eliminate interference and reduce power consumption. In optimal beamforming, analog and digital beamforming are combined with optimal algorithms. Optimal beamforming in massive Mimo systems meets the requirements of next-generation wireless communication systems. Multi-user Mimo users benefit digital beamforming in LTE Advanced Pro and in 5G NR. 5G base stations may use analog, digital and hybrid beamforming. For example, inside an analog beam, digital beamforming may be used for spatial multiplexing. For example, this figure shows the use of spatial multiplexing to transmit to two users over a single analog beam. Beamforming improves the array gain and the diversity gain. The use of beamforming has many advantages for mobile operators, users, and the environment. Moreover, it enhances network capacity, coverage, energy and spectral efficiency, as well as the user experience. Beamforming enables dynamic cell coverage to meet the needs of fast-moving users, and those in areas where network coverage is not satisfactory. Beamforming also ensures uniform data speeds and latency across the cells, especially in densely populated areas. Higher order modulations may then provide higher data rates to serve distant users. As a result of the extended coverage, the base station density decreases. It is also possible to use Mimo beamforming for indoor Wi-Fi systems and for coupling from outdoor to indoor environments. Beamforming with multi-user Mimo can maximize transmission in the desired direction while simultaneously eliminating undesired user signals. In the millimeter wave band, narrow beams and shorter ranges provide security and privacy as well as better protection against interception, interference and jamming. Reconfigurable intelligent surfaces. Traditional wireless systems regard the radio channel as an uncontrollable entity that scatters waves randomly, behaving like a wide range of surfaces along the propagation path. Wireless channels can be controlled by strategically positioning reconfigurable intelligent surfaces, or RIS, between transmitter and receiver to maximize the range, and to improve the link quality, the reliability, and the efficiency of wireless systems. RIS is a programmable surface structure that controls the scattering of electromagnetic waves by altering its electric and magnetic properties. Metasurfaces and conventional antenna arrays can be used for implementing RISes to control signal characteristics such as reflection, refraction, absorption, radiation pattern, and polarization. Metasurfaces consist of two-dimensional arrays of structural elements which are electrically thin and dense. The size of these elements is much smaller than the signal wavelength. RISes can also be implemented by electrically tunable antenna arrays with large numbers of low-cost elements that operate as scatterers with no need for RF chains. RIS structures are commonly placed on walls to redirect incoming waves using their adjustable radiation patterns. An electromagnetic wave incident on a RIS is first absorbed, then processed by a microcontroller, regenerated and transmitted in a specific direction. Besides controlling electromagnetic scattering, metasurfaces can also be used for data modulation, signal processing, and storage of electromagnetic pulses for short periods. In this manner, RISes may improve the availability of cellular and global navigation satellite system signals in areas where they are not easily accessible. RISes may increase the network's efficiency by deflecting the incident electromagnetic waves so as to shorten the path to the receiver, and to regenerate cellular radio signals, and forward them to indoor users. RIS applications are expected to become common practice as the 5G and 6G frequency bands migrate into the millimeter wave and terahertz regions, as signals in these bands attenuate rapidly and cannot penetrate walls. Applications of Mimo systems. Mimo systems have revolutionized wireless networks by significantly increasing data rates, coverage, efficiency, and reliability. 4G and 5G networks extensively utilize them for improved performance. Mimo technology can also be used for enhancing the performance, increasing data rates, improving link reliability, and reducing interference in military communications, satellite communications, and underwater communications. In IoT applications, such as smart homes and industrial automation, as well as healthcare monitoring and smart cities, Mimo systems enable efficient communication by supporting multiple simultaneous connections. Mimo-based radar systems provide significant advantages in terms of target detection, tracking, and imaging. Using multiple antennas, these systems are capable of enhancing spatial resolution, mitigating interference, and improving target discrimination in complex situations. Mimo technology can also be used in electronic warfare systems to counter electronic countermeasures, including jamming, interception, and signal intelligence. Conclusions. Widespread use of internet, cellular radio and other digital services led to proliferation of the users, the demand for higher data traffic, and requirements for improved services. These led to the development of novel and reliable communication techniques. Mimo systems provide a great opportunity to provide cost-effective solutions to these issues, and to meet requirements for power and spectrum-efficient communications. Operation in millimeter wave band greatly facilitates the use of massive Mimo systems, which embody diversity, beamforming, and spatial multiplexing as special cases. In addition to enabling efficient and secure wireless communication as in cellular and IoT networks, Mimo systems also contribute to the enhancement of military capability. For a comprehensive understanding of this groundbreaking technology, make sure to check out our white paper, Mimo Systems, Diversity, Beamforming, and Spatial Multiplexing, on our website. Master essential concepts of wireless communications in a flash with our online course Quick Connect to Wireless on Udemy. Keep up with the latest breakthroughs in information and communications technology. Subscribe today and stay ahead of the curve.